Okay, we're going to do the second section now, which is called fixed point iteration. This is, I'm going to say, a slightly odd method that kind of initially feels like it's a bit like magic. I will be kind of going through a bit about where this comes from, but it is a slightly strange method. It comes underpinnings is from this first bit, first idea that you will have come across. So I've got this equation, one of the ones at the start, which I said it's a cubic. We could solve it in the calculator, but there's no obvious method of doing it algebraically. And we are going to do it numerically. To be honest, that's how the calculator does it too. So we're kind of replicating that. Okay. I'm going to rearrange this equation to make x the subject. But I'm not going to make x the subject in a way that makes sure there's a number on the other side. I'm going to allow there to be x's on both sides. There are actually lots of different ways that you could do this. But I'm going to show you one of them. So bear with me for now. So my first method is this. I'm going to say x cubed plus 1 is equal to 3x. I'm taking x onto the other side. And I'm going to divide both sides by 3. X is equal to, I divide both sides by 3 and switch the order. Okay, so x is equal to x cubed plus 1 over 3. Now, actually that means that if x satisfies the original equation, it will also satisfy this equation too, because all I've done is rearrange it. So you could imagine that if I was to sketch both x and x cubed plus 1 over 3 on the same axes, we know that intersections of those two lines is also a solution to the original graph. Intersections of functions is also the same as solutions to the graph. So I'm going to show you what I mean by that. This is x cubed minus 3x plus 1. I'm going to add x cubed plus 1 over 3. And I'm going to add y equals x. Now, if you look very carefully on this graph, you will see that wherever y equals x and x cubed plus 1 over 3 intersect, i.e. here, here, and here, they actually perfectly line up with a root of the original cubic. So to say that again, any points where y equals x, so I've got that from here, and y equals this, if they intersect, we also have a root of this equation. So I'm going to write that down. Intersections of these are a root of x cubed minus 3x plus 1 equals 0. Okay, so that might at first go, well, so what? What's the point in that? Well, you're going to have to be patient a little bit. I'm going to show you, though, again, that we can actually just do this a different way. So I could just choose a different rearrangement. So another rearrangement that I could do is I could say, what if x cubed is equal to 3x minus 1. So I take the 3x and minus 1 onto the other side. And I could say divide both sides by x squared, and I get this. So there's another one. I'm going to sketch both of those functions. So there you go. This is the original function, y equals x, and now 3x minus 1 over x squared. Not a graph that you would have to be able to know how to sketch, but it's this line, and it looks a bit strange. But once again, if you look really carefully at where the intersections of this graph is, there's an intersection between 3x minus 1 over x squared in purple and y equals x. It's directly above where the solution to the equation is. There's another one here, right next to where there's a solution, and right here, right next to the solution. So the idea is, if I could find where these graphs are intersecting, if I knew the x value, I would actually have found the roots of the original equation. So if I can find places where y equals x equals 3x minus 1 over x squared, I would have found x values that solve the original equation. Okay, again, how are we going to do that? Hold on one more minute. So just as a third option, there are often plenty of different options. Here's another one I could have done. I could have gone to x cubed equals 3x minus 1, and I could cube root each side. So that is, yet again, another option. And if I was to sketch that, it would again intersect in the same places. Right. So what you do is you form something called an iterative formula. You form something that is called an iterative formula. So recap, I got my first rearrangement that I did there a minute ago is I came up with this. Not quite. X cubed plus 1 over 3. So I'm actually going to form an iterative formula. My iterative formula, which you will know about if you have done sequence series. If you haven't, I will briefly explain what I mean by it as I do it, but you might need to go and look at sequence series chapter to kind of really get it in full. I'm going to form this iterative sequence. I'm going to say x sub n plus 1 is equal to x n cubed plus 1 over 3. And what that means is, I'm going to form a sequence of numbers. If I need the next term in the sequence, I put the previous one into this equation to get the next one. The previous term into this equation to get the next one. I'm going to do an example of that in a second. So if I had my other rearrangement, for example, I had this one. Again, I would just take the x on the left-hand side and I would make it xn plus 1. And on the right-hand side, I'm going to make it 3xn minus 1 over xn squared. So again, if I want the next term in a sequence, I put term into the right-hand side to get the next term. You will, of course, need the first term in the sequence. You will need the first term in the sequence. So on the screen now, I have a little picture of a zoom in of the line y equals x and the line y equals, this one is x cubed plus 1 over 3. Okay, I'm just going to show you that that is really what I've got there. So what I've done is I've zoomed in to this section here. I've actually turned off the other graph, but we know that there will be a root underneath it. So I've got this picture here. So what in previous into this point I've said is that if I can find where this point is, which is over a point about here, this will be a root of the equation that I'm trying to solve. So if I can find where that is, if I can find where that coordinate is, then I can find where that is, and I've found the root and I've solved it. So my iterative formula is xn plus 1 equals xn cubed plus 1 over 3. And this is where this all starts to come together. What I'm going to do is I'm going to start with a point that is near the root that I want, not the actual root that I want. I'm going to start with it near. And in fact, to illustrate this really clearly, I'm actually going to start with one that's not even that near. I'm going to start with 1. And I'm going to take my initial guess at where this root is to be 1. So x0 is 1. I'm now going to use the iterative formula to try and calculate the next values in this sequence. I'm going to rub that out because I'm just getting in the way. Okay, so x1. So I'm going to put x0 into the right-hand side, and x1 will be xn plus 1. So I'm going to put 0 into the right-hand side and get x plus 1 out. So x1 is going to be x0 cubed plus 1 over 3, which in this case is going to be 1 cubed plus 1 over 3, which is 2/3. So actually, we've gone slightly closer. We've moved slightly closer to the root that we're trying to find. But why is that? Why has that worked? Why has that worked? Well, I'm going to show you on this graph what's happened. So, I put x equals 1 into my equation. I'm actually going to switch the mouse here. I put x equals 1 into my equation. And I can't quite put it into the right place because it's snapping to the grid. That's annoying. I might just draw it by hand. Okay, so I have put x equals 1 into my equation, and it goes all the way up to y equals x. So I started here, and then I've put it in, that was my x0 at 1, and then I put it into the equation of the red line. And what that effectively did is it found the y value here. So that's given me the y value 2/3. So you can see the y value of this point is at 2/3, 0.66, about here. So that's my x1. So that's what I'm doing. I'm now here on the picture. Now I'm going to try and find x2. To find x2, I'm going to put it back into my iterative formula. So it's going to be x1 cubed plus 1 over 3. So I'm going to put 2/3 in there. So that's going to be 2/3 cubed plus 1 over 3. And I've calculated this in advance. And you get, well, you get a fraction, but you get about 0.432. 0.432. So what does this look like on the picture? Well, what I've done is I've put the y value here back in to the equation of the curve. So somehow I have to get from the y values over here down to the x value that's equivalent down here. Well, to do that, I'm going to go via y equals x, because what does y equals x do? It makes y equal x. So I'm going to go from y down to x. So a way of seeing that is I've gone horizontally from here across to there, and then down to there. And this is 0.432. Looks about right. I'm about 0.432. So this was at 2/3, and now I'm about 0.432. So I've kind of started drawing a staircase where I'm going up to the curve, along to y equals x, and bouncing off it back to the curve. And what that does is it takes the y values, puts them back in at x, gets a y value, puts it back in as x, gets a y value, puts it back in at x. That's what the effect of bouncing y equals x forms. But essentially, I've started from the point and I'm bouncing between the curve and the curve and y equals x. So actually, if I wanted to calculate x3, it should be by going along here and then back down to the curve there. That should be my x3. So here's x0, here's x1, and x2 and x3, and I'll carry on like that. Have I got that right? Actually, x1 is here. Here's x2, 0.432, and then I'm going to keep bouncing between the line and the curve. And now you might see how we're actually going to find this root. Because as you keep bouncing, you kind of zoom in on this root. So it should be the case that this sequence will converge to the root that we're interested in. But let's see it numerically. So that's it on a picture. Let's see it numerically. Let's use a calculator to do it. So I'm going to form my iterative sequence. My iterative sequence is x. So the way I'm going to do it, actually, I'm going to use the answer button. So I'm going to make 1 equal to the answer. So this is how we do this on a calculator. This is how you do it in an exam. You might have a sketch. Make 1 equal to the answer. Then I want to cube it, add 1, and divide by 3. So I'm going to, using the answer button, I'm going to type that in. Answer. I'm going to create a fraction to make sure I'm going to write it in the right way. To the power of 3 plus 1 over 3. Now, since answer was 1, if I click equals now, I should get 2/3. I do. Now, if I just click the equals button again, it should take the answer, which is 2/3, put it back in, and get the next one out. So I should get 0.432. Well, I get the fraction, which is 0.432. That's my x2 value. So I can now just press equals again, and I'm going to get x3. So let's do the next one and let's write it down. x3, 0.360. So x3 is equal to 360. Yeah, 3602. And let's have a look. Does that look about 0.3602? It does. This value here looks below this one. That's my x3. Here's my x2. And here's my x1. So I've got my x3 is there. And you can see it's getting closer to the root. I'm going to stop writing them down now. I'm just going to press equals over and over again. And you'll see it has converged to the root of that equation. This is the answer to that root. And the more I click equals, the closer and closer it gets. Okay, that is a fixed point iteration. In an exam, you would have to just write down your x values. You might have to form the iterative equation first by rearranging, and that's the kind of thing that we're going to do. Okay, there's a different kind of picture. So this is what we call a staircase picture. There's another kind of picture that you get called a cobweb. So I'm going to show you how we might get a cobweb example. So I'm going to go back to my picture. I'm going to zoom out. I'm going to turn on that other graph. So when we had this picture, when the lines were kind of y equals x and the other line were kind of going in the same direction, we ended up with a staircase. If we get one where they're kind of going in opposite directions, you end up getting a slightly different picture. So I'm going to do this one. I'm going to try and find a root. I'm actually going to end up finding this root. Note that I don't actually have that much control about which root I find, which is interesting. But I'm going to try and find this root, and it's where that intersection is. So that's my picture. This root, and it's that intersection. I'm going to start again, as before. I'm going to start at x0 is equal to 1. So my new iterative formula is xn plus 1 is equal to, and this one is the 3x minus 1. So it's 3xn minus 1 over xn squared. I got that from the previous example. I'm going to take x0 to be 1. So x1 is equal to 3 times 1 minus 1 over 1 squared. So it is equal to 2. And let's see that on the picture. So I start at 1. I go up to the curve. I go either left or right until I find y equals x. So y equals x is there. And you can see I've ended up at 2. So I'm over 2. So this is going to be x0 and x1 is at 2. Let's do x2. This is going to be 3 times 2 minus 1 over 2 squared. And at this point, because I know that what I'm going to do in this on the calculator, I'm going to start putting it on the calculator. So I'm going to put 1 as my answer. 1 is now my answer. I'm now going to type the equation that I want. So I'm going to create a fraction. It is 3 times answer minus 1 over answer squared. So that should give me the next one, which is 2. I knew that was coming. The next one, 5 over 4. So this is 5 over 4. Let's see it on the picture. So what's happened there is we have gone down to the curve and across to y equals x. And then we should be at 5 over 4. Yeah, that's about right. That looks like x2, which is at 1.25. It's 5 over 4. Okay. Now you can see we're kind of doing a different thing to a staircase now. I can actually just finish it off on the picture. I can actually see what's going to happen, and then hopefully it's going to be replicated in there. I'm going to keep going to the up and down to the curve, left and right to y equals x. Up and down to the curve, left and right to y equals x. Up to the curve, across to y equals x. Down to the curve, across to y equals x. Up to the curve, across to y equals x. And this is an alternate way that it's going to find the root. But it is going to find the root, which eventually should be somewhere here. This is called a cobweb picture. Let's see it on the calculator. So we should end with a root in kind of 1.5-ish, around there. 5 over 4, and I would write these down on my to show I've done the iterations. There, there, there. We're going backwards and forwards. You'll notice it's going backwards and forwards as it's going around and zooming in on the root. It takes quite a lot longer than the other one. Cobwebs can take a long time, but it is converging to the root of about 1.532. And we found the root. Right, what can go wrong? So there are dangers that can go wrong. The main danger at this point, this kind of method, is that it can diverge. Divergence, and I'm just going to write it on the screen and show you an example. Okay, so you need a starting point. So this is a very similar picture to what we had before. Actually, this is showing the first iteration that I did. Now, the key is that I can change the starting point. So if I change the starting point, you'll see I get different kind of staircase going there. Now, the danger will be is if I go over here. So if I start over here, if I zoom out, you'll see that the staircase is kind of zooming off up there. And what it does is it diverges, and it never finds any root because it diverges off. There's actually a kind of a proof of why this is. It will be if the gradient of this graph here, if g of x, or the rearrangement function, is greater than 1 at the root. So because that is greater than 1, the blue line is steeper than y equals x, it zooms off, it diverges. Okay, so that is how this fails. It can just diverge off into nowhere and you can get nothing. I can demonstrate this on a function like this because you will just see the numbers blow up and then they stop working on a calculator. I think I will leave it there for you to kind of practice and see where those examples can happen. I am going to give some suggested questions for you to have a go at. So this is exercise 10b, and I recommend you have a go at questions 3, 6, 7, and 10. It is worth noting that you sometimes, I'm not going to do this exam question, but this is what an exam question might look like in these kinds of questions. You might have to rearrange some equations to find the iterative formula. Use the iterative formula to find some x1, x2, x values and give them to 3 decimal places. You might try and find where the intersection is. And then finally, and this is why I showed this to you, you might need to actually draw a diagram or draw on a copy of a diagram the actual kind of cobweb or staircase that comes from these kinds of questions. So that is fixed point iteration. It's a slightly odd method. It is slightly odd. It feels a little bit like magic at times, but it does come from some proper grounded mathematics. That is fixed point iteration. I'm going to end the video there.